Welcome to a new Atlas YouTube live talk. My name is Rebecca González Suarez. I am a member of the Atlas collaboration, and today I'm going to be your host. This is a live talk with a Q&A session at the end, so make sure that you ask questions, any questions you have. And for that, you can use the chat here, or you can use our Instagram stories where we have a little question box set up, or any of our social media channels. We are ready to try to gather them all together. And then we will pass some of them to the speaker. I mean, depending on how much time we have. But feel free to ask as many questions as you have. So this is actually the 11th talk in our series of live talks. So we already come a long way. So do check the playlist that you can find also in our channel to watch them all. And this one, once it's finished, also will join them. So you can just come back over and over again. So now that I give you this small information, let's pass by our speaker. So our speaker today is Dr. Hideyuki Oide. Hideyuki is a high-energy physicist working at KAK, the main facility of particle physics research in Japan. He obtained his PhD at the University of Tokyo in 2013, when he also joined the Atlas collaboration that same year. Dr. Oide's current research focuses on the search for exotic new particles that make use of the full innermost Atlas detector system. He is also working in the construction of a next-generation silicon pixel detector for the Atlas experiment. And without further ado, Hideyuki, please go ahead.
Okay, thank you very much, Rebecca, for the introduction. And yes, hello everyone. Today I'm coming in the KK's Communication Plaza, hosting a kind of very public exposition of the accelerators or detector facilities. It's a very nice place to, when you have a chance to visit KK. Okay, so then today I'm going to talk about the search for longer particles, and then maybe just let me start from something that's slightly different. So that during the last 2 years, I was not able to join the CERN, visit CERN, and then just a couple of weeks ago, there was a chance. I finally got a chance to visit CERN. These days, the visit is a slightly longer flight, and then as you can imagine, it takes 14 hours of flight, and then after the flight, for most of the people, it's common that it's very tired. I get very tired. So after landing, I need the relaxation some case, and then one of the best ways that I found out is that taking a bath. Then the very good bath is a hot spring. And then one of the nice things in Japan is that we have quite plenty of the hot spring places everywhere in the land. And it's not only us and human being to enjoy this hot spring, but also this cute monkeys are also as well. Now, I really think that these hot springs are really present everywhere in the country, but this is not really coming just from any source of the heat. And then hopefully everyone will know that this kind of hot water is really coming from the heat from the underground. We have magma and volcanoes, and then the hot water is basically boiling underneath. And if you look at the country, Japan, we have really literally hundreds of the volcanoes are present. And then the downside is we have a very quite frequent earthquake, but this is a very good side of living in the country. But then there's one question here. So what are the heat sources of the Earth? Without any heat sources, the volcanoes are not present, active. And then naively one can think that this heat source may be coming from the beginning of the Earth. That at the really birth of the Earth, the Earth is a kind of the really melted rock, and then the heat is cooling down over the billions of years. Then maybe it's a residual heat are present. However, if only the heat source is such kind of primordial one, the Earth can really cool down extremely quickly, and then we cannot really profit in a this kind of comfortable temperature. So that we have an extra amount of heat, and that is coming from the radiogenic one. And then recent researchers just clarified how much of the heat fluxes are coming from primordial source and from the radiogenic. And then, yeah, best estimate basically tells it's basically half and a half. So this radiogenic source is a really non-negligible part of the Earth's heat, and then we also profit from this kind of heat via the hot spring. Now, thinking about the radiogenic source, that we have basically the three major radioisotopes present, and the majority is coming from the uranium and tritium. And then these radioisotopes have some lifetimes of several billion years, and then this basically determines the Earth's summer history. Now, so this comes to the word that some introduction that the radioactive sources and then how this heat is actually generated. So the heat of the radioactive nucleus is actually generated by its decay. So the radioactive isotopes are unstable, and with some lifetime of the billions of years, they actually get to the stabler isotope, and then this cascade decay will be eventually turned on to the heat from the Earth. Then the study, we know that this kind of decay has two types called the alpha decay in the left-hand side and beta decay in the right-hand side. And then what is important for the particle physics is that the left-hand side is connected to the so-called strong force, and the beta decay is connected to the so-called weak force. And these two forces are not really, how to say, commonly let's say, familiar to everyone's daily life. But this is very important because they are fundamental forces. And then in physics, we ask what are fundamental forces. We know so far 4 fundamental forces are present. And then probably the electromagnetic force and the gravity you are almost very familiar with. And then we have just spoke about the strong force and the weak force. And then the strong force is named because it's a stronger interacting than the electromagnetic force. And the weak force is named because it's much weaker than the electromagnetic force. So the physicist naming scheme is a kind of very simple and somewhat naive. But here we have a very important big questions. Why there are 4 types of these different forces that we don't know? How these forces act to matters, or how are they similar kinds of other forces present in the universe? We don't know these kind of things, and the very big questions that particle physicists are basically trying to answer ultimately. Okay, so from next slides, I'm going to get a slightly deeper part of the particle physics, but then before getting to that, I'm just going to introduce some of the terminology about the energy scale and length scale. So we basically use a little bit special energy unit called the Electron Volt. And this is basically the kinetic energy of an electron gained by 1 volt of the voltage. So they assume we have some battery here, and then they're having the electrodes, and the electrons will be accelerated through the electrodes, and then they get some kinetic energy. And if this corresponds to 1 volt of the electrical voltage, we call this 1 electron volt. And then since we go to the very high energy, 1 electron volt is just too small, and then we found of using the larger energy unit, and the 10 to the 9th, which is 1 billion electron volts, we call it the 1 giga electron volts. That's a 1 GeV. And similarly, 1 TeV is the 10 to the 12th electron volts. So it corresponds 1 trillion electron volts. Okay, now we also have a particular amount of energy corresponding to a length via the following relation. So the energy is coming in the left-hand side, and then this lambda symbol is the length scale. and a bridging between the length and the energy. Okay, that sounds a little bit counterintuitive, but with a very fundamental physics constant called Planck constant, where it's used for the quantum mechanics of describing how much the world is pixelated. And then the right-hand side, we have a speed of light. Also, this is very fundamental physics constant. And these two fundamental constants bridge between the energy and the length. So we basically say that what energy is the length, inverse of length, and length is inverse of energy, such like that. Similarly, we also express the mass of any particle using the energy. And this is a famous Einstein's relation, bridging mass and energy. We're using the speed of light as a constant. And so we also express the mass of the particle using a unit of the electron volt. Okay. Okay, having introduced our terminology, I'm also going to introduce our accelerator, the LHC. And then, as you may know, that LHC is the world's largest proton collider, and its circumference is 27 kilometers. And then we had this shut down in the last 3 years, but this year we restarted, so-called round 3. And then inside this tunnel, we have under the 100 meter underground, we have this 8.3 Tesla superconductor magnet, and this is bending the proton beams. And then the achieving colliding energy is 13.6 TeV. This is achieved that record. And then the collisions of the protons happening is extremely frequent. It's a 1.5 billion collision per second. And then using this machine, we can literally produce all of the standard model particles that we know. Okay, so then I come to the brief introduction of familiar standard model particles. This is we basically think that elementary. So the left-hand side is the particles all for the matter, and then this is divided into quarks and the leptons. And the quarks are having 6 types divided into 3 generations, and each of them has 3 colors. Leptons do not carry colors, so it's only kind of gray one. And then also the 3 generations are present. Electrons are somewhat the most familiar to everyone, and then the rest is kind of the heavier electron, heavier tau or mu. They are heavier electrons. Coming to the right hand side, these are some particles corresponding to the force in the terms of particle physics, and the photon is the mostly familiar. It's basically light or electromagnetic wave. And this is doesn't have any mass. While for the gluons, the top is the responsible for strong interaction, and then in the bottom we have double boson or Z boson, which are corresponding to weak interaction. And then last and not least, we have a Higgs boson, and this was newly discovered in the LHC in the 10 years ago. So this is this year's 10th anniversary of the Higgs discovery. Okay, and then this, what is important for particle physics is just not counting the type of the particles. Of course, that's important, but also what is important, we have the physics framework underneath. And then just briefly saying that this all of the standard particles are really based on the 2 important fundamental physics concepts. One is the special relativity that Einstein has developed, and the other one is a quantum mechanics. And these 2 physics concepts are kind of very separate one, but somewhat it is possible to make a hybrid between the 2, and that will make the so-called quantum field theory. And then this is a really fundamental part of the theory backbone we have underneath the standard. Okay, so that's a kind of picture of today's particle physics, but I just like to get back to some years back to the 1930s. And then there was the era that we didn't know that such a large number of elementary particles are present. And the world was a little bit more simpler, that we have an atom, and then we have nuclear, and the electron is circulating around. That was already established. And then inside the nucleus, the people already knew that we have proton and neutron present, and then the electron. And then we have electromagnetic interaction, and the photon is present. So this is really the simple picture of the world. And then we had just two different forces in question. One is a strong force, and the other was a weak force. For strong force, we have some different story that I don't speak much, but just today like to focus on the weak force. Okay. So the weak force, as I explained, that this is related to the beta decay of the isotope, and this weak decay, beta decay, was really this is strange. So it is known that the neutron decays to proton and then emits an electron. So let's say particle type changes, and that is already very strange. But moreover, if we take a look at the energy spectrum of this electron from the decay of any nuclei, it has a broad spectrum, and this indicates that somewhat the energy is missing somewhere. And then at first, people might thought that energy conservation law is not really conserved, but here we have the Wolfgang Pauli, who said, no, it's energy is rather conserved, but rather we just miss the particle that we don't see. And he basically predicted there is an additional neutral particle that isn't visible, and that is nowadays we call neutrino. So this is a first picture of the beta decay we have got, but then the physics of interaction is not known at all at that point. Now later, Enrico Fermi was a kind of genius in particle physics, and then he basically devised an idea to make a pairing of the neutron to proton, and then think that this particle neutron is convertible to proton, and likewise electron is also convertible to neutrino. And then this is a kind of a flow of the weak force. Then behind this kind of idea, there is electromagnetic interaction understanding, and this is in some sense mimicking the electromagnetic interaction. But the difference here is that there is a very different interaction constant from the electromagnetic interaction, and that is called the Fermi constant. And then if we write out the constant, it's like this kind of value. And since this is 10 to the minus 5, it's very small, then we say that this interaction is really weak. So, but behind the scene, what is happening is really unclear. And then, this Fermi constant, it is already giving some hint at what is happening behind. So, since that this kind of interaction is really pairing the particles like neutron to proton, and underneath neutron proton there is a down quark and up quark present, and likewise inside the electron there is a pair, the neutrino and the electron. And then this kind of pairing is can be considered behind this constant, we would have some resemblance with the electromagnetic interaction. And if we put let's say fundamentally that there is a constant is something similar to the electromagnetic interaction, then we can basically assume some energy scale is present under it. And then the calculation, a simple calculation basically tells that this interaction scale should be around the order of the 100 GeV. And then if we get to this picture, the weak force is actually not really so weak, because the real constant size is similar to electromagnetic interaction, but there is something hidden underneath, which is really heavy. from the typical scale of the weak interaction. And this presence of the weak scale is a really true physics that we understand as of today. And then there are many decay of the particles, and that is related to the weak interaction. For example, the neutron beta decay lifetime. We know that it's approximately 15 minutes. And then if we write down the equation how this lifetime is determined, we basically have the mass of this weak scale on the numerator. While the interaction energy scale is a really small compared to that, it's only 1.29 mega electron volts, and it's 1, 2, 3, 4, 5 orders molecular small. But despite this very, let's say, 1.2 mega electron volts is something we have in daily life. This interaction actually proves that something very high energy scale. Likewise, the muon decay lifetime, which is 2.2 microseconds, and this is very different from the 1,000 seconds of neutron lifetime. But still, basically the same rule applies here. And then the muon lifetime also that looks at the scale of the interaction. So the important point is that low energy phenomena point to a high energy fundamental energy scale. And then this is becoming important in the later part of my talk. Okay, so we now know that the hot spring we profit, also this killed monkeys also profit, is really connected to the weak interaction scale. And then this weak interaction scale is, however, very problematic in elementary particle physics, because we basically don't know why and how this weak scale is present in the universe. So there is difficulty in understanding the fundamental scale. We only have so far well-established two scales. One is the scale that the gravity meets the quantum mechanics. And this calculation tells that it's extremely high in energy. It's at 1.2 times 10 to the 19th giga electron volts. And then this basically it's only happening in the very beginning of the universe. And then we also have this weak interaction scale. And then this weak interaction scale is a very high energy. It's just 100 GeV. But still, compared to this very high energy of the very beginning of the universe, it's 10 to the 17th orders of magnitude different. And then basically, the standard model doesn't really tell at all that why we have this kind of very large gap of energy in the universe, and these are both extremely fundamental. Then basically we don't have an answer as of today. And then I said that the Higgs boson was discovered 10 years ago, and that was a very, of course, very great achievement for our field. But given the fact that this Higgs boson is present as a standard model predicts, and then also we have not found any extra discovery of any new particles so far. And this situation is really constructing this problem much more than the starting of the LHC, I would say. So there's the situation that we stand today. And then the question is what we do now. Okay, so that was a bit about the theoretical part of the particle physics. I just now come to the detector part. So the Address Detector is really a huge detector, gigantic one. The length is 45 length, and then the height is 20 meters high. And then beams are running in horizontally, they're like a yellow arrow, and then coming to the front and then make a collision in the center of the detector. So this is nice CZ view, but the real detector is something like this. So it's really like a building that was scaffolding, and then the superconducting magnets are running, and then there are many this kind of planes around. And these planes are not really just a building block. it's a really all of them that built as a detector. So it's a looks like a wall that's a really detector, and everywhere is really covered by detectors. Now, taking a look at the cross section of this detector, it's a really like a multi-layer cylindrical structure, and then it is largely separated into three big parts. The innermost is called the inner tracking system, and this is mostly for the drawing traces of charged particles within a very strong magnet. And the second layer, relatively larger part, is called calorimeter. And basically, this is a really thick wall with the sensors, and then responsible for the stopping particle showers. And then that enables to measure the event energy flow and the shape. And then the outside, we have extra detector called the muon spectrometer system. And then the point is that energetic muon cannot be stopped by even with this kind of thick irons. So then, so we can basically measure only muons outside this thick wall of the calorimeter. And then if we have this kind of detector system, basically we can differentiate the interaction of the known standard particle that can actually be captured by this kind of detector system. And then it's all designed to capture and distinguish all known visible particles within the standard model. And then collision events are analyzed by measuring energy and momentum of these visible particles. So that is how the detector is designed based on the standard model. But the question is, what if the new particles phenomena imprint inside the detector is very different compared to these designed behaviors? Now, we are going to search some new particles present in order to obtain any hint to solve the fundamental questions. Then the LHC has been learning for the decade, and then searching for mostly targeting heavier particles. Heavier particles, I mean, is heavier than electroweak scale that I mentioned. It's around 100 GeV and more heavier than that. Then most of the theories basically predict that these particles are since really heavy and they tend to decay lighter particles. They decay to lighter particles in a very prompt manner. Prompt means that with a very insignificant amount of time. However, just taking a look at a broad view of the particles we know so far, not only just the elementary particles like quarks and leptons, but also taking account the composition particles for the mesons or baryons, etc. These particles, we know that there are some visible lifetime, and that they are really scattered in the wide range of lifetimes and in the lighter masses. So that's a situation of the standard model we know. But the searches in the past have been a bit lacking in the area that in the green region here. And then this is mostly because the kind of focus was present in a really heavier range of the searches. But actually, our detector is also capable of making searches and taking account of this having some finite lifetime of particle. And then this is a kind of exciting journey in the recent years, because it covers really wide scenarios to explore of the new physics. And then also it has technical hurdles because the detector is capable of making the search, but they're not really designed to do this primary. So that we need to have some extra work in order to use the detector for such kind of searches. And then the third, this is also important that such kind of the detector events are really significant. That in terms that we don't have any similar event present in this inside a standard model. So it's extremely clear to say yes or no for the discovery. And that is very important for making a research work and experiment. Okay. So when we say that we want to search for long lived particles, but how the long lived particles can be present in the physics beyond the standard model, and then just try to depict some possible cases as an illustration. And then first case is that really mimicking the idea of that the Enrico Fermi has devised for the weak interaction understanding. So suppose we have some new particles somewhere around within the reach of the LHC energy scale, but these particles produce and then eventually decay to some standard model or some other particle. But this decay, suppose if this decay only is only possible through some new particle that is present at much higher energy above the LHC reach. And then in this case, as they're very similar to the relation between the neutron decay that is observing the weak interaction scale, this kind of the interaction is a very kind of weak, so to speak. So if the interaction is weak, there is a plenty of a chance that this kind of particle can be have a very visible amount of lifetime. So this is one of the case that we can think as a very possible case of the scenario. The other case is just simply assume that this kind of new particle involves very new force, which is very weak. We call it feeble, just in order to differentiate from the standard model weak interaction. But if that is the case, yeah, the chance that the particle feels that kind of force per unit time is really small, then that it can be wrong. And this kind of the scenario is also the interesting in terms that we may have a chance to also clarify the meaning of the so-called dark matter. So the right-hand side picture is recently taken by the James Webb telescope and taking the deep, far deep part of the universe, and then you can basically see the galaxies are kind of really warped, and that basically is a strong indication that we believe that dark matter is present quite abundant in the universe. And then particle physics wise, we have so far very little clue about what this dark matter is, and then that is also a very true motivation that we want to explore further. And then such a feeble interaction may be also connected to the dark sector that we want to probe, because the feeble interaction means that it is hard to discover as well. And then one may wonder that if such a very weak interaction, it can be really possible fundamentally, but we know the gravity is extremely weaker than the electromagnetic force, and then we don't know the reason of it. So then, yeah, assuming something fundamental new force involving the very weak interaction is not extremely odd assumption, given that we are already living in a kind of very odd world. Okay, now I can come to how we carry out the long-lived particle searches using the LHC, but just for illustration, I come to the particle physics of the experiment in 1970s. The technique is very different from the LHC detector nowadays. It's called bubble chamber. And then if you go to CERN restaurant 1, there is a public area in the outside, and still this detector is exposed in the outside, and very nice object. This bubble chamber with a beam injection, it will make an interaction inside this chamber, and then you can make a very fascinating traces of particle like this kind of the right-hand side picture, and literally we take the photo. And then these traces of particles are really hinting what kind of particles are produced, and then they decay. But just having lines, it's a little bit puzzling. Just make a quick explanation. The yellow lines with the visible white lines are the charged particles. And then if we make this charge produce somewhere in the middle, then it is possible to make the connection between this disappearing point and appearance point. And this, we basically believe that some invisible neutral particles fly in between. The idea of making the long-lived particle search in the LHC is a sort of modernized version of bubble chamber experiments. So the idea is similar to what we have carried out in the bubble chamber experiments. So firstly, the long-lived particles must be produced in the collision point of the proton collisions. Then the long-lived particle flies outside. And then we have a sensors inside the trackers, and that will make an array of hits. If this long-lived particle is visible, that means that electrically charged. And then eventually this particle may decay somewhere in the middle, depending on what the lifetime is. But there is a kind of chance that this kind of trajectory traces of particle is very different from the family of particles. And if that is the case, there is a chance of directly observe this kind of particle. But there are some cases that this particle is not really electrically charged. And in that case, within this kind of tracking system, there is no trace. It's basically invisible. But since we have suppose there's some final lifetime, and if that lifetime is sufficiently short to fit within the detector length, and then this particle decays, and this, somewhere in the sudden, some familiar particles appear, and then we can see that, okay, from nothing else, nowhere, something has appearing, and then that is must be connected to production in primary collision point. And this kind of topology is very different from what we usually observe in the standard model. So that is one of the key signature we are able to hunt. So, but here is a problem that such decay signal is, since it's not covered within the standard model, we by default, the data analysis usually drop this kind of the signature as a noise in the data analysis. And in order to read that and tag this kind of the decay as present, the special and dedicated data mining techniques need to be applied. Okay. So then we have this detector structure, and then that is kind of already present and not easy to replace easily. But making use of this detector technologies, it is possible to have a quite various way of the searches, and then that can be classified into two. One is that detection of charged long particle detection, and that is possible for the lifetime over approximately 0.5 nanoseconds or longer, where the particle traverses multiple layers of detectors, while the indirect decay detection. So where basically this kind of approach is possible for the shorter lifetimes than 10 nanoseconds, let's say 10 or 15 nanoseconds. So these are two complementary approaches we can take in principle. Just to say that these scales are all that we bridge the time and length using the speed of light, because most of the cases these particles really fly similar to the size, to the speed of light. So we gauge the length with time, or likewise the time is gauged by the length, vice versa. And the experiment we say that this is a natural choice of the unit. So since this kind of long particle decays or detections really different from what happens in the standard model particle phenomena, this gives us a kind of advantage that escaping from background events. So low energy standard model events are generated very frequently, while the new physics events are quite rare. Then otherwise, it's very frequent than we have already discovered. In many search sectors, some standard model events are quite confusing, or even very difficult or impossible to distinguish using the cutting edge data analysis, employing the machine learning, etc. as of today. So the clean environment is also always helpful for that data analysis, and then it's with the less confusing events always welcome. And then most of long-lived particle searches really suffice this condition. So that means that once this kind of new particles really produced, then it is really likely that we can claim the kind of discovery. Okay, so the last part of my talk, we'll just introduce one example searches of that kind of thing, which is called the new particle target is called Neutrino. And this is a hypothetical partner particle of the gluon. Gluon is a massless, zero mass gauge boson responsible for strong interaction. And then in some cases of the theoretical scenario, this gluon can be long-lived because we basically assume that this gluon can decay to other particle only via very heavy particle, which is not directly accessible from the LHC reach, but that only the decay path is connected with this bit. And then this gluon can be long-lived. Since that this kind of gluon is a strong interaction, it can actually couple with the light box and then can carry electrical charge in some case as a group of particle called our hadron. So this kind of particle fly inside the detector with either neutral particle, either as a neutral particle or as a charged particle. So this gives us a chance to search for this kind of particle in two different ways. The method A call is a case that this particle is charged. Then the particle is visible and it traverses the tracker and make some hits on the sensors of silicon layers. And then important thing is that since if we assume this particle is really heavy and then heavier than 1 TeV, the speed of this particle is much slower than the other standard particles, and it's only like 50% of the speed of light. And this is compared to other standard particle extremely slow. Okay, so that gives us a very distinctive signature. The method B is the complementary, and then trying to tag the displaced spray of this standard model particle within the tracker somewhere in the middle. So we cannot really easily make a trace of the original gluon particle here, but then the decay is significant. So we are able to reconstruct this kind of the event. And these two searches are complementary. So this is a state of the result that we have got in 2015. And then the method A is coming here. And then that is probing somewhat the intermediate lifetime range around let's say 1 nanoseconds to 10 nanoseconds, and even longer up to this very stable cases. And then the method B of the decay tagging method, which was probing much higher mass up to the 1.5 TeV or 1,500 GeV. Then within the LHC round 2, we accumulated a much more of the data, and that gained a lot of sensitivity. And the picture as of today is something like this. So the method A is reaching to the up to the 2.2 tera electron volts of the mass as a limit that of the search, while the method B is coming to the up to the 2.4 TeV of the mass reach. And then the important thing is that the lifetime range coverage is different and complementary between H2 searches. Unfortunately, we are not discovering this type of particle yet. But what I can stress here is that this value of mass, like a 2.4 TeV, is really the highest mass reached for this particle search compared to the other prompt analysis, for example. It's limited up to the 2.0 TeV. So I would say that this kind of search is really pushing the energy frontier that the LHC is achievable. And then this is just one example of the long-lived particle searches that we Atlas experiment is carrying out. the thinking of the how this kind of particle will decay, or the how this kind of is produced, we can think of the quite many patterns of the very exotic and striking signatures. And then each of this kind of analysis involves some special techniques to how to tag this kind of the special events. That is not always very easy to do, even to record these kind of events. So the entire collaboration is getting more and more involved in this kind of researches these days, and then that is getting to the really exciting field nowadays. And the last message from me is that this area of research is also very promising. That as I said, that it's a very clean experiment, and then that means as we gain more and more data of the collisions, then the search sensitivity actually grows up. And this is the year projection of the future plan of the LHC, that how much of the data we are going to accumulate is this blue line. And then from this projection, we are only standing at let's say 5% of the total accumulated data we plan to take up to the end of the life. So this really gives us the right research path that we may really future discovers a very fundamentally exotic new particle in the future using the very great machine of the LHC. So that comes to the really end of my talk. Thank you very much for the joining to the session until the end.
Thank you very much. This was a very, very beautiful talk. So I would like to ask our audience in YouTube to ask their questions, because the Q&A session is about to start. So if you could stop sharing the screen so we can see you. Okay, I think yes. I can do it myself. Okay. There you go. Excellent, very good. So then I think we can start the Q&A session with some questions that we have already gathered from during your talk. But again, really very beautiful talk, very nice, and it was very enjoyable. All right, so let's start by one question that we got from Instagram from Cat Light Travel. So is the LHC the only place that is looking for new lonely particles?
Oh, so the question is if the LHC is the unique place that they discover. It really depends on the mass, I would say. So the energy reach really determines that if we can directly produce such a new particle. If the mass of such a new particle is really heavy, then effectively the LHC is the own unique machine that can be accessible as of today. Now, yeah, there are some areas that the people are seeking. The much lighter lonely particles may be present that we having seeking the lower energy part in the past era of the particle physics, and then we thought that there is no presence of such particle, but there may be something that we may be overlooking, and some people or some experimental projects are also trying to seek lighter lonely the new particles also present, and that gives more chance that the smaller scale experiments may have some chance of the real important discovery.
All right, very good. So thank you so much. So now we're going to go for one a little bit more generic. So this one is from Hailey Stevens, also from Instagram, and the question is from someone who wants to get into particle physics, what is the best way to begin?
Oh. So that's an important sort of question. So let's say depending on the universities, but I think the physics courses are present in the many area of the department everywhere. And then when you start undergraduate, this really basic concept of the physics you learn. And then once you get some interest in general, then you can want to study further. There may be the graduate school that you could enter. And then at that point, the real research work involved in the particle physics may start if you choose the specialization of particle physics experimentally. So indeed, inside Address experiment, there are quite many numbers of the students working and very active. So they are, let's say, very core researchers of the experiment. They're very important. Without their, let's say, tireless efforts, that many of our physics research analysis is not able to really publish. And then so that means that let's say the length of your career is not really important. But that passion is more important to really pushing forward the frontier of the. So if you are thinking of the particle physics as your let's say journey of life, then that's a very nice selection, I would say.
And I agree with you as a particle physicist myself too. So that's a very nice answer. Thanks so much. All right, so then I think we can take now a question from here, from YouTube. So for example, we have Safa Guide on YouTube asking, how can we improve the trigger system for better inputs? I guess, better inputs to the analysis. So it's a good one.
Okay, so I suppose that this question is very advanced. Just to explain what the trigger is. So I think that I spoke in somewhere in the slide that we have approximately 1.5 billions of the proton collisions per second, and then even with the extreme fastest cutting edge electronics of the data taking machine, we cannot really take this total amount of the energy. And then so we have to really select from some prejudice that what kind of events are really interesting in. And then when this LHC experiment has started, of course the really hunting target was the Higgs boson first, and then also the known standard model, and then also heavier prone particles. So that all of this kind of electrical system is really targeting such kind of thing together. Now, of course, still this baseline data taking system is very important, but we are kind of more eager to take some, not to miss the chance that something is really happening, interesting happening, we might be missing. So then the experiments are really nowadays expanding any possible channels that we can open with using the small amount of the data taking resource, but if that is really designed to be neat and specialized, then there are chances to open more of the channels that we have been missing so far. So this kind of efforts have been also carried out intensively in the long shutdown that we have had in between 2018 and 2022. And then we now restarted the data taking from this year, and then maybe the harvest may come up in after the several years of data taking. So that's my answer.
Okay. Well, thank you very much. I think we're gonna take another one also from YouTube now. So this is Kiera on YouTube, and is asking, what long-lived particles are the hardest to look for? Because this matches a little bit the previous question, right? Could we change the experiments to see them better?
Okay, so that's also a very important question. I would say, I would answer that what is really hardest that what we have not imagined that such kind of particles were present. So if we assume something, the new exotic one is present, then we can prepare, take data. But if the phenomenon is something, we even don't imagine, then there is no way to think of such thing. So I would call that such things is really difficult and even not really possible to carry out as of today. So that's might be a kind of answer.
All right. So thanks for that answer. So, okay, but then we can maybe now take one question from our Instagram audience. So Ernie I on Instagram has asked us, how do we separate possible new long-lived signals from neutrino signals?
Sorry, say again. It's a muon signals and the
So
neutrinos.
how can you separate possible long-lived signals from neutrinos?
Oh, long-lived signals from neutrinos. That's okay. So the question comes to the what kind of neutrino we are going to have. It's if it is a standard model, it's a little bit delicate question, but if that is standard particles, then yeah, neutrinos may sometimes interact with the detector, but it's very extremely rare chance that we may capture neutrino inside the detector, so it's not visible. But we also have some potential beyond the star model physics scenario that there may be some heavier neutrino present, and then if that is the kind of heavier neutrino is present, and that might be connecting to the early universe, we may also have a chance to see. And actually, there was a recent search that we have published about searching for this heavy neutrino search. So it depends on the assumptions, but if that is a kind of heavier one, we also have a chance to discover.
Yeah, that's a very good answer. I thought exactly the same when I was reading the question, that you know, we have the heavy neutrinos that could be quite an uninteresting long-lived signal, actually. All right.
Yes.
So let's see what all questions we have. All right, so let's ask you one more that just came now from YouTube, that is from Direction. So it's asking us, what are your thoughts on the Galactic Center gamma ray excess? Are there reasonable long-lived particle models that are compatible with this observation?
Oh, that's really
Yeah.
I'm not quite sure if I have the prompt answer. So the interpretation of this galactic center gamma rays is also somewhat model dependent, but there are cases that we think that real particles that can be produced in LHC can be relevant to that. So and then there are also sectors of such as that they're only really focusing on such cases, and then really having a strong connection with the dark matter motivation. So yes, there are areas of such that we can do for that kind of interest.
All right, that's also a good answer, right? I mean, this is like a little bit out of our field, but it's good to find these connections with other kind of problems and different kind of physics. All right, so let's go for another question that we have on YouTube from Minastrat. And the question is, are there ways to go look at all data, maybe from other experiments, and search for new theoretical particles?
Yes, so all the experiments that I assume that it's not only just the LHC, but also other type of experiments that usually where we collaborate with other experiments is we bring basically first carry out each experiment can do, and then within the conferences we basically discuss what's the implication of this each other to the other experiments. So basically that's a active interaction that we regularly do inside conferences, etc. And then if something more specific as a task is possible, we figure out, then some collaboration team bridging the different experiments will launch at some point with some limited time, and then they basically take some kind of task to try to make a combined statement between two, like Address and also at the counterpart CMS experiment do this kind of the combined statement sometimes, but not always happening in the such new particle such hunting area as a regular, because usually the experiments, the two experiments are really trying to compete each other to make a better results. So then the analysis design is not always really the natively thinking of the combining at the later part. So that's somewhat different from the, for example, the spaceless measurement of the Higgs boson. But that's a kind of the interesting possibility that we may need to think in the future to make a much more sophisticated combination of the scientific statement.
Thanks so much for the answer. And we are getting close to 1 hour now, so we are going to start to wrap up. I'm just going to have a couple more questions that we have. So one more from YouTube. This one is from Amelia. And the question is, what if the new particles are so long-lived that they can never be seen in an LHC detector?
Okay, so this is also the case that we basically think that if we don't have any, let's say, prejudice about the length of lifetime, and then if that is really long, and then we cannot really capture it. It really looks like similar to neutrino. So then we basically observe such kind of thing as a missing energy inside the detector. So in some area of the detector, that there is an imbalance of the energy activity. And then, of course, the standard model phenomenon also produce such kind of events. So the differentiation is a little bit difficult than the really directed detection of the detector. But if there's such a phenomenon is happening in the really some abundant, we may see that some more of the such kind of the missing energy event, and that may eventually does not fit with the standard model prediction. And then we may need to call, okay, something extra must be present. Then that is kind of the potential scenarios that we could think of. The question is how to identify what this particle is. That's a more difficult answer, probably.
All right, that's a very nice answer again. And I think now for closing, one of the last questions that we had in YouTube, I think is important for everybody. So Kira is asking, most important question, what are the cool exhibits behind you? So tell us.
Oh, so yeah, it was tough. So the country was a kind of the closing in the last 2 years, or almost 3 years, and then going to CERN was kind of the difficult. In the last seasons, it was a kind of relaxed, and nowadays it's not possible to visit CERN and then there was a really nice experience for me as well. And then during this COVID situation, we have been using this kind of remote the meeting system from the past, but we only limited the communication inside Zoom, and then that actually makes some changes. Good side of the changes that a lot of the seminars are actually present nowadays inside world. Everywhere we can connect everywhere, and I would say that this live kind of session is also increasing in the world. So that's one side of change. But the other side of change is that the physical meeting is not really frequent. And then if you already have a kind of established connection of the working style with the other persons, that other collaborators, that the research works of progress is not really bad. But if you really like to make something new with a new people, with a new occasion, this is very suppressed. So there are differences in a good side and bad side. And then since we also experienced some good side of this remote connection, the situation might not resume to the real pre-COVID situation. We should really profit from the new technology or the communication styles, but we should not really forget about the importance of the physical meeting and also the real communication with the people. So I'm a bit sorry that I cannot really see audience's faces from the video camera today, but really I'd like to see me too physically next time.
All right, so thank you very much. It was a very nice talk, very nice Q&A session. I think it's time now to wrap it up. So thank you really very much. Thanks to everybody that has connected via YouTube. As you know, this is gonna stay here. You can come back to the talk more times. And yes, have a good evening, good afternoon, good morning, depending on where you are in the world. So thank you so much and goodbye.
Bye-bye.
Bye.